This is a video about constrained optimization, how you maximize a function of several variables when you actually have constraints on the function that you're trying to maximize. Let me give you some examples from economics so you can get an idea of how important this technique is. First and most important, I guess, is the maximization of utility subject to income and price constraints that the consumer has to obey in order to maximize utility. There's a very similar problem in minimizing costs subject to a production function and input price constraints. There's maximizing firms' profit subject to price and production function constraints. So this is a really important topic, and there is a mathematical technique for dealing with these constrained optimization problems. Let me explain a little bit how the technique, which is called the Lagrangian Theorem, that uses something called Lagrangian multipliers, how this Lagrangian theorem works and what it is. So here's a standard problem. We want to maximize utility, which is a function of the goods consumed by consumers, and we're going to assume there's just two of them, spaghetti and tacos, following on from the example of the last video. And you want to maximize utility subject to a constraint that says that income is equal to the total amount of money you spend on both goods together. They have given income and given prices, so there's a price of spaghetti and a price of tacos. PS is the spending, PS times S is the spending on spaghetti, and PT times T, price times quantity bought, is the spending on tacos, and that's going to be equal to the consumer's income, I. The theorem says that the solution to this constrained optimization problem, that is maximizing utility subject to the income constraint, can be found by creating a new function, and the new function we'll call U star. And the new function is the original function that you wanted to maximize. Make a new function which is the sum of u and a Lagrangian multiplier. And the Lagrangian multiplier is equal to a constant that we'll call, and is conventionally called, lambda, I guess to remind you of the L in Lagrangian, times the constraint, in this case the income constraint, written in a form that the income constraint is equal to 0. So we form this new function U star. It's equal to the utility function plus lambda times the income constraint written in a form that's equal to 0. So we want to write this function as PSS plus PT T minus income. We want to call that I here. So this function U star is called the Lagrangian function, and the Lagrangian theorem says that if you find the optimum values of the variables in the Lagrangian function using the unconstrained rules for optimization, you'll end up finding the rules for maximizing utility subject to whatever the constraint is. And so now we want to maximize U star, the Lagrangian function, with respect to changes in S and T, the two variables in the function. So the way to proceed with that is to compute the partial derivative of U star with respect to S, the partial derivative of U star with respect to T, and the partial derivative of U star with respect to lambda, the Lagrangian multiplier. And this is an unconstrained optimization problem. We want to set these partial derivatives all equal to 0 and see what the resulting rule is for maximizing utility. So the partial derivative of u star with respect to s, that's going to be the partial derivative of f with respect to s, which we recognized from the last video, is the marginal utility of spaghetti, plus the derivative of lambda times ps times s, that's going to be lambda ps, and that wants to be equal to 0. And then the same thing for t. The partial derivative of the Lagrangian function with respect to t is the partial derivative of f with respect to t, which is the marginal utility of t, plus now the partial derivative of this Lagrangian constraint function with respect to t, which is going to be lambda pt, and that's going to be equal to 0. And when we take the derivative, the partial derivative of u star with respect to lambda, that of course is just going to be the constraint, ps s plus pt t minus income is equal to 0. So let's look at this for a second. We can solve this equation for minus lambda, and that's going to be equal to the marginal utility of s divided by the price of s. And the second equation we can also solve for lambda. That's going to be minus lambda equals mut over pt. Now, since two things equal to the same thing are equal to each other, we see that the rule for maximizing utility is mus over ps is equal to mut over pt. Written this way, it says that you want to maximize utility, buy quantities of the goods that make the marginal utility of the goods per dollar spent on each. The marginal utility of spaghetti divided by its price is the marginal utility you get from spending another dollar on spaghetti. And you want the marginal utility per dollar spent on both goods to be equal. You can rearrange this if you wish. This is t. You can rearrange this if you wish to show the marginal utility of spaghetti divided by the marginal utility of tacos is going to be equal to ps over pt. So ps over pt, that's the slope of the budget constraint. Marginal utility of s divided by the marginal utility of t. That's what we identified previously as the marginal rate of substitution of s for t. So this says you want to maximize utility, choose amounts of the goods that make the slope of the indifference curve, the margin rate of substitution, equal to the ratio of the prices of the goods. Now what we want to explore in the next video is what else you can do with these results. Notice that marginal utility is a function of both s and t. The income constraint is a function of both s and t. The prices, ps, pt, and income, are all givens. If we solve this system of two equations, one equation here, a second equation here, solve these two equations and two unknowns for the values of spaghetti and tacos, what we end up finding is the consumer's demand function for those two goods. In other words, embedded within the solution to the utility maximization problem is the derivation of individual demand curves for goods. And what we'll find, of course, is that those demand curves will depend on prices, income, and of course tastes.